Every family, as you know, has both similarities and differences, and the same is true in chemical families as well. So we're going to look today at the reactivity and the properties of a family of elements, specifically the halogens. And the halogens here are in group 17, so the well-recognized fluorine, chlorine, bromine, iodine, and the not-so-well-recognized astatine, which is a radioactive element. Many of those, we hear about them constantly. People know about chlorine because of its use in disinfectant and pools and so on. People have heard of iodine, again, because of its use as a disinfectant. And there are clear trends in the properties of the halogens. Chlorine is a gas at room temperature. Bromine is a liquid at room temperature. Iodine is a solid at room temperature. So right there you have already the beginning of a periodic trend in the properties of the halogens. And we want to look today at a periodic trend in the chemical properties of the halogens in terms of their reactivity. And in particular, what we want to do is see if we can, first of all, is there a trend? Is there a pattern? It's possible there isn't. But if there is a pattern, what is it in terms of the reactivity, comparing the reactions of chlorine, bromine, and iodine? Now, we're not going to use fluorine. Fluorine is extremely toxic, extremely difficult to work with, so we're not going to do that. And astatine, as we mentioned, is a radioactive element. But once we study chlorine, bromine, and iodine, we're going to be able to infer from that the reactivity of both fluorine and astatine. So let's go back over here, and I've got a lot of bottles set up here. Now, your first thought is, wait a minute, I'm going to work with chlorine, bromine, and iodine. Obviously, I need a well-ventilated lab. Do we have the hood on? Let's put the hood on, because we're going to get started here. And I'm working here under a ventilation fan. So can you hear me all right over that fan? Okay, good. You can easily prepare in the lab very dilute solutions of chlorine, bromine, and iodine to make it safe to work with as either a demonstration or as a student laboratory where you can do it on a very small scale. I'm going to do it on a little bit of a larger scale today using about 10 milliliters each of chlorine, bromine, and iodine water. But you can also do it with 10 drops of chlorine, bromine, and iodine if students are doing this. So the first thing I want to talk to you about is how to prepare freshly prepared solutions of chlorine, bromine, and iodine in the lab to prepare just as much as you need so that there'll be none left over at the end, and you can prepare it fresh within 2 to 3 days of when you want to use it. Chlorine is prepared by the reaction of sodium hypochlorite, which is bleach solution, with HCl. And you know, that's one of the warnings, the safety precautions in working with sodium hypochlorite is never add acid to it. Well, the reason for that safety precaution is that it does generate chlorine in aqueous solution. So if you want to do this on purpose, you're making a very dilute solution of chlorine. And so it makes it easy to work with, and it's safe to work with as long as you're working in either a hood or a very well-ventilated lab. So those are important precautions. Similarly, you don't have to buy a lot of bromine and store a lot of bromine because you don't want to store a lot of bromine. It's going to corrode all of your storage areas. So you can freshly prepare just as much as you need a dilute solution of bromine in a very similar way by taking a sodium bromide solution with sodium hypochlorite and some HCl. And that generates a dilute solution of bromine. And we're going to see from the colors just how dilute these are. Now, iodine, you don't have to do this. You can take iodine, which is safe to store, and you add a little bit of sodium iodide because it doesn't dissolve just without any added sodium iodide. So what I said, that's how you would prepare the solutions. And I'm not going to do that. We've already done it. What you want to make sure that you do is that you put it in a glass bottle, preferably, and actually what we definitely recommend is a PVC-coated glass bottle. An amber bottle will protect it from light, and that's very important. Even if you're going to be using this within 2 to 3 days, it's extremely important to remember to label everything with the hazard warning and the name so that there's no doubt about what you have. The worst thing is to have a bunch of bottles in the hood with no labels on them. So even if you're freshly preparing it, take the time to prepare a label for it, and you can make just as much as you need for one demonstration or 4 demonstrations, whatever it is. So I'm going to put on some gloves here. What we're going to do is compare the reactions of halogens with sodium halides, okay? And I've written a generic equation here that tells you what we're going to do, and we're going to do a series of reactions of chlorine, bromine, and iodine with the other sodium iodides. So in general, we're going to take a halogen, X2, and X and Y can either be chlorine, bromine, or iodine. So we're going to take the halogen, react it with a sodium halide aqueous solution, 0.1 molar. These are very dilute. And what we're going to observe is, do we get a different halogen produced? And the way that we're going to be able to distinguish that is by the colors, and we'll see that as soon as we get started. Now, we don't know. These are not all going to take place. These reactions will only occur in this direction if X is more reactive than Y. And so this is the way that we're going to be able to discern the pattern in the reactivity of the halogens, because these reactions will take place in one direction only. They're so-called single replacement reactions. So I'm going to start with chlorine water. Actually, I'm going to start by taking the caps off all these bottles. Okay, I'm going to start with chlorine water, and for the first one I'm going to measure the volume so that we're doing things approximately the same. And I've got 10 milliliters of chlorine water, and I'm going to pour that in the first, and then for the second one I'm just going to pour to about the same level. Okay, I'm going to go ahead and cap that up. I'm then going to take bromine water and add that to my second 2 bottles here. And already you can see a difference in terms of the color of these solutions. And again, these are safe to work with in a well-ventilated lab because they're so dilute. And I've got a 0.04 molar solution of iodine. Now, the way that we're actually going to do this reaction is in a 2-phase system. So you can note the initial color of the halogens in water. This is a very, very pale yellow-green. I don't know if you can pick up the color. It's not white. Let's see if that helps it any better. Just to compare the initial color of the chlorine, it's got a very pale tint to it. Got a yellow-orange solution for the bromine, and then for the iodine, more of a reddish-brown solution. What I'm going to do is add 20 milliliters of hexane to each one of these, and we're going to compare what happens. So again, I'm going to do what I did before, which is I'll measure the first one and then pour to approximately that level for the others. And this is hexane. Hexane is less dense than water, so when I add that to the solution, I get 2 layers. I'm just going to add to approximately the same level here. Now what I'm going to do at this point is cap these bottles because I want to look at the distribution of the halogen between the aqueous layer, which is on the bottom, and the top layer, which is the hexane. And to do that, I'm going to want to pour. I'm going to want to shake them. So I'm going to do that, and I'm going to just shake each one and then set them down and let them separate. And one of our favorite presenters had a phrase that he used. He said when he does something, something interesting will happen. And I think the first something interesting that you see is just in the distribution of the halogen between the two layers, okay? And I'm going to come around here so that I can see what you see. In the chlorine, we had a very, very pale solution, and it looks like the color is in the top layer as well as in the bottom layer there. So we've definitely seen some of the halogen go into the organic, the hexane layer, which again we said is the top layer because it's less dense than water. But notice the bromine. So already we can say something about the solubility of bromine. Is bromine soluble in hexane? And the answer is yes, obviously. And you could even ask your students, do you think bromine is more soluble in water or more soluble in hexane? And based on the color of those two layers, you would say that it's more soluble in the hexane layer than in the water layer, which is something interesting. Now, these two are a little bit harder to see, but can you see the color of the upper layer in these two that had iodine initially? The iodine solution, remember, was a reddish-brown color just in water. The iodine in hexane is interesting because it's actually a violet color. In this case, pretty deep violet color, okay? So those are just our halogens, but you need to remember those colors because what are we going to do next? What we're going to do, we said, is take the halogen solution, in this case a two-phase system, and we're going to react it with the other sodium halides. And we're going to observe the color changes. And from that, we're going to be able to tell whether or not X was more reactive than Y. So in the case of the two chlorine bottles, we're going to react it with sodium bromide in the first one, sodium iodide in the second. In these third and fourth bottles, I have bromine. I'm not going to react it with sodium bromide, so I'm going to react bromine first with sodium chloride and then with sodium iodide. And how about the iodine? What am I going to do there? I'm going to add sodium chloride and then sodium bromide. And what we're going to look for is any evidence of a chemical reaction. So again, I'm going to measure the first one and then I'll add approximately the same volume. This is sodium chloride. Actually, I don't want sodium chloride. For the first one, chlorine, I want to use sodium bromide and sodium iodide. Just for now, I'm going to take this away from here so that I can more easily pour, and then we'll put it back at the end. Again, what we're going to look for is color changes in both the bottom layer and the top layer. That is, any evidence of a chemical reaction. So you should have a really good picture in your mind of all of these things. So I've got sodium bromide. I'm going to add that to the chlorine. Already something interesting has happened. And I'm going to take the sodium iodide and add to the second bottle with the chlorine, remember. Again, something interesting has happened. Now, in the case of the bromine, I'm going to add sodium chloride and sodium iodide. So sodium chloride to the first one. And sodium iodide to the second. Again, something interesting happened. And now to the iodine bottles, I'm going to add sodium chloride. It obviously helps if you're doing this as a demonstration for your students. You'd want to put a data table on the board and have your students fill out the data table as they go along. So I added sodium chloride to the first one and sodium bromide to the second one. And let's cap those up so that we can shake them and mix them. Okay. Now, does everybody remember exactly what these looked like? Is that nothing? Okay. Let's put that back up there. Remember, the first two bottles contained chlorine water, and we had two very, very pale yellow-green layers, almost colorless. Well, obviously, the chlorine reacted. To the first bottle of chlorine, we added sodium bromide. What is the product when chlorine reacts with sodium bromide? It's bromine, and we can see that from the colors, right? When we had the initial bromine solution, it was yellow on the bottom, orange on the top. So clearly, chlorine has reacted with sodium bromide. How about the sodium iodide? Here we had, again, two colorless layers. We added the sodium iodide. What did we produce there? We got a purple color in the top layer, a dark brown color in the bottom layer. We obviously produced iodine. So clear evidence of a chemical reaction for chlorine reacting with both sodium bromide and sodium iodide. How about the second one, the second pair? Here we had bromine water in both 3 and 4, and bromine water was yellow on the bottom, and the hexane layer was a darker orange. This was bromine with sodium chloride. Did anything happen there? It doesn't look like it. That looks the same as it did originally. So the bromine did not react with sodium chloride. Now, did the bromine react with sodium iodide in bottle number 4? Yes, because clearly we've produced that violet color on the top in the hexane layer and that brown color. And if you want to be, how do you know it reacted? Well, compare 2 and 4. Here we had chlorine with sodium iodide. Here we had bromine with sodium iodide. The bottles look, given that there might be a little concentration difference between my chlorine water and bromine water in terms of how I prepared it, they pretty much look identical. Similarly, this was chlorine with sodium bromide. We produced bromine, and that looks just about identical to bottle 3, which had bromine with sodium chloride. So that means the bromine did not react with sodium chloride, and it's just the original bromine, but here we produced bromine. So already we've learned what? That chlorine reacted with both sodium bromide and sodium iodide. Bromine only reacted with one. It only reacted with the sodium iodide. How about the iodine in bottles 5 and 6? Did the iodine react either with sodium chloride in bottle number 5, sodium bromide in bottle number 6? So clearly, those iodine bottles have not changed. We still have that darkish, reddish brown color on the bottom layer and a purple violet color on the top layer. So notice that iodine is actually a different color in water than in hexane, and I think most students find that kind of interesting because they think color must be an intrinsic property, but it's not. Okay, so what have we learned? We've learned a whole lot. Remember, let's go back to the board. We said that these single replacement reactions of a halogen with a sodium halide would take place in one direction only. And if X2 is more reactive than Y2, then you would get Y2, and the other sodium halide. So we know that chlorine reacted with sodium bromide, reacted with sodium iodide to give bromine and iodine respectively. Bromine only reacted with sodium iodide. It did not react with sodium chloride. So already we know that chlorine is more reactive than bromine. And because bromine reacted with sodium iodide to give iodine, then we know that bromine is more reactive than iodine as well. So a whole lot of information, interesting color reactions. And again, if we go back to the periodic table, we can now discuss that trend that we talked about in the reactivity of the halogens. So chlorine was the most reactive, bromine less reactive than chlorine, but more reactive than iodine. So clearly in the nonmetals, at least in the halogens, we would say that the reactivity increases as you go up the table. So remember we said that we weren't going to react with fluorine for obvious reasons, and we're going to go into that as well. Would you expect fluorine to be more reactive than chlorine? Yes. And in fact, it's an interesting story, although it's a little macabre, I don't know. But, the halogens, chlorine, bromine, and iodine, had all been discovered by 1830. They don't exist in nature in their free element form, but they had been prepared in their free element form, that is, as Cl2, Br2, and I2, by electrolysis or electrochemical methods. So by 1830, all of those free halogens had been prepared. Now, fluoride was well known as sodium fluoride and so on. Calcium fluoride, fluorite is a mineral, very abundant mineral. But fluorine had not been. And that's because, and this is the macabre part of the story, everyone who tried to make fluorine by the same method that was used to make chlorine, bromine, and iodine, they all died in the course of the preparation. Finally, in 1886, a French chemist named Henri Moissan was able to prepare fluorine by taking the appropriate precautions in terms of preparing it in stainless steel vessels or in copper vessels that have been coated with something. Obviously, if exposure to even a small amount of fluorine is toxic, it is deadly. So we know that's an interesting story in terms of the reactivity pattern that we just talked about. You know, the periodic table is the most celebrated icon or symbol of chemistry across the world. Everybody recognizes a periodic table. But it's important in teaching chemistry to really get across the full value of the table in terms of our understanding of chemistry, because that's the power of the periodic table. I mean, it's a nice, all of the things are nice, but the power of it is its predictive ability, its power to predict properties of elements. So let's see if we could predict something else. These are the halogens, fluorine, chlorine, bromine, and iodine, as we said. Could we, not even studying it in the lab, could we predict what the reactivity of the neighboring elements should be, that is, oxygen, sulfur, selenium, tellurium? Well, based on the same pattern that we saw here, we would predict that oxygen would be much more reactive than sulfur. And in fact, that's true. We know that oxygen, even though we live in an oxygen environment, it's a strong oxidizing agent. So again, you have the power to predict, based on studies in one family, the properties of elements in another family. And that's really, I think, the most important lesson we need to teach our students is the power to predict and explain. And of course, if you go on, you would explain the reactivity of chlorine, bromine, and iodine in terms of the electronegativity of those elements and in terms of some of their other properties. So this is a demonstration or a lab that I call All in the Family, because we're clearly looking at similarities and differences within a chemical family of elements. Thank you.